this lecture we're going to continue off where we dropped last time. So in the last class we had solved this particular equation, and in this particular class we're going to start off with the generic form. By this generic form I mean the matrix is not hard coded, but A, B, C, D are four values. Okay, so the equations are u equal to a times x plus b times y and v equal to c times x plus d times y. We're going to make a quiver plot of this particular 2D vector flow, and after that we're going to plot the stream plot of it. Okay, and because we are going to pass a b c d as four parameters, I have gone ahead and made a function which wraps everything inside this function, and I'm going to make an interactive widget which takes as an input a b c and d. Okay, there's nothing very difficult. I've just modified the previous program and I've removed the eigenvectors so that when things become complex we have something to work with. So let me run this cell. Okay, so this is the plot that we have, and just by looking at this plot we can see that there is one distinct eigen direction like this and another distinct eigen direction like this. Okay. And let us now change the parameters and see what happens. So when C is changed, so I've printed out the eigen values over here. Okay, so let me just go over here. Okay, so before proceeding, the eigenvalues of a matrix A can be found out by using np.lineal.eig. So this is the function that returns the eigenvalues lambda and the eigenvectors v. And the nature of the eigenvectors is such that eigenvectors returns a 2D array and v1, v2. So all the rows of one column correspond to one eigenvector. So this is one eigenvector. And v3, v4, so this is another eigenvector. So all the rows of the second column, this, it represents the second eigenvector. So this is all rows of the first column, and this is all rows of the second column, and the indexing starts from 0. That should be obvious. So this is how we can extract the eigenvectors as well. So with the help of the eigenvalue and eigenvector, we can clearly see where the flows are going. Okay, so let me just go back to the original case. Okay, so over here the eigenvalue 2 corresponds to the direction 0.7, 0.7, that is essentially 1 comma 1, and the eigenvector minus 3, rather the eigenvalue minus 3 corresponds to the eigenvector minus 0.24 comma 0.97. So it's like if we draw this direction 1 comma 1, it is this, and this is corresponding to an eigenvalue of 2, so it's unstable. This is the unstable manifold, while this particular thing, so minus, so y is 0.9 and x is minus 2, so something quite steep. So this corresponds to the stable manifold because it corresponds to a negative eigenvalue. So as t tends to infinity, the trajectories are attracted towards the unstable manifold like this. Okay, this is something which we had discussed in the previous class. Now when we change the values of a and a, b, c, d, the eigenvalues change, so do the eigenvectors, and correspondingly the flow also changes shape. Okay, there's nothing quite difficult about it. Okay, for example, in this we can clearly make out that this is one eigen direction. Okay, and this is the other eigen direction, and this eigen direction is stable while this is unstable. Okay, but what happens when things become complex? So let me increase the value of d. All right, something weird happens. So we no longer have stable or an unstable thing going on, things tend to look like a spiral. Okay, so for d equal to 3, we do have real eigenvalues 2 and 2, but they're degenerate eigenvalues. Okay, so this is a special case. Let us look at this particular case. So the eigenvalues are 1 plus j and 1 minus j. In fact, if you're doing it for such kinds of matrices, if you're finding out the eigenvalues of such kinds of matrices, you're bound to end up with complex conjugates. Okay, so this is the complex conjugate of this. So we know that the solution x, it grows as c1 e to the power lambda t in the direction of v1, and c2, this should be lambda 1 e to the power lambda 2 t times v2. We know that's just a linear combination of this, and once we diagonalize it, so finding out the eigenvalue is tantamount to diagonalizing it. So the solution grows along this eigenvector with a rate of lambda 1, and the solution grows at a rate of lambda 2 along the eigenvector lambda 2. But what is going on when the lambdas, they become complex? So lambda 1 comma 2 can be written as alpha e raised to I, or rather plus minus I theta. So this is like the polar representation of a complex number. We're essentially representing this in a polar form. So e to the power lambda 1 comma 2 t is simply going to be e raised to alpha t times e raised to plus minus I theta t. And the meaning of this is some, so alpha is obviously real. So this is representing that in time, how does the magnitude of e to the power this reduce? Actually, it will be clearer if we substitute uh, this over here. So we have x is equal to c1 e to the power alpha t times e to the power I theta t v1, and this will be plus c2 e to the power alpha t times e raised to minus I theta t times v2. And by using the De Moivre's theorem, we can sort of write this as cos theta t plus j sin theta t, and this thing as minus j sin theta t. So effectively, uh, x becomes some sort of a linear combination of v1 v2, some linear combination of v1 v2 times c1 e to the power alpha t, and some other linear combination of v1 v2 times c2 e to the power alpha t. So essentially we have the amplitudes of this x reducing in time or increasing in time. So if alpha is positive, the magnitude of these terms, they grow, and this linear combination obviously involves cos theta t and sin theta t. As a result, we have a rotationality over time, meaning if we have a vector like this, and if you multiply it by cos omega t, this vector will start changing its direction. Okay, so in time, multiplication by cos theta t and sin theta t, it starts making this vector rotate. So that is why, so look at this origin. So origin is obviously the fixed point. So origin is always a fixed point for a linear system, and because of this eigenvalue alpha over here is positive, so the magnitude of this grows and the thing begins to rotate. So if we look at a trajectory, it's spiraling out. Okay, all the trajectories seem to be spiraling out. So it starts near the origin, and it will start rotating and its magnitude will grow. It's something like this. Okay, now if that eigenvector becomes negative, rather not the eigenvector but the eigenvalue corresponding to this alpha. Okay, if this this real part, if it becomes negative, let us see for what combination we can have that. Okay, so for this particular combination, we do have a negative value of we have a negative real value. So it means that in time the amplitude decays, and so it's spiraling inwards, but the amplitude is decaying. In fact, if the eigenvalues are purely complex, then this particular flow, so there is no change in amplitude because of this alpha t. If alpha becomes 0, there is no change in amplitude, and as you can imagine, if you have two vectors which are rotating, it will simply go off as a circle or a closed orbit. It's not a circle, it will be a closed orbit. So the conclusion is, if the eigenvalues A have zero real part, that is real part of lambda is 0, then it it boils down to a closed orbit where the fixed point is still the origin. If the real part of lambda is greater than 0, then it is a spiral out. If the real part is less than 0, it's a spiral in. Okay, I'm not going to go into the elaborate theory of it, but you can look up the book by Strogatz. Okay, so the reference to the book will be there in the description. So I'm showing you how we can get it done using a computer. Now the other case that is quite useful is when the two eigenvalues become equal. Okay, when eigenvalues are equal, which mean that the system will look something like this. Okay, this has equal eigenvalues. Then what happens? Let us see. Let us change the slider and see. So when A and D become equal, uh, and the other two things become 0. Okay, it's not showing any plot. Oops, this have to be 0. Okay. Okay. So when the two eigenvalues are equal, in this particular case it's equal to 1, we see that the center is sort of emanating trajectories all over the space. Okay, so this particular case is called as a star. So the origin is still a fixed point, but in this case all the trajectories originating from the origin are repelled at equal rates away from it. This is distinct to this particular case where the manifolds were the attracting or repelling ones, but everywhere else the trajectory, depending on how it's a linear combination of the two eigenvectors, its trajectory was dictated. But in this particular case, all the trajectories are equivalent, and the reason is quite simple. So if we have two eigenvalues, then any vector can be written as a linear combination c1 times v1 plus c2 times v2. So where v1 and v2 are two eigenvectors for this system, and when we substitute this form inside x dot equal to ax, what do we have? It is equal to a times c1 v1 plus c2 v2, and this becomes equal to c1 a v1 plus C2 A V2, but A V1 is equal to lambda V1 and A V2 is equal to lambda V2, and both are equal because we are considering the case where the eigenvalues are equal. Okay, so in that case this becomes lambda times C1 V1 plus C2 V2, but C1 V1 plus C2 V2 is simply this vector x, so this becomes lambda x. So this means x dot is equal to lambda x, and so the solution for x is e to the power lambda t times x. And this means that all the vectors are exponentially growing or decaying depending on the sign of lambda. Whether lambda is less than 0 or lambda greater than 0, the vectors in that entire phase space will either grow exponentially or decay exponentially, or the trajectory will blow away exponentially fast or decay exponentially fast. In this case, the eigenvectors are both positive. Now let me go to this particular case. When they are both negative, we should have a attracting star. All the trajectories should converge to the origin, as we see over here. Okay, so this is the condition for having a star, and all these cases will be quite useful when we analyze non-linear systems. Like I've already said, understanding linear systems is like the first step towards the analysis of a non-linear system. The last interesting part is that of a degenerate eigenvalue. So a degenerate eigenvalue means that you have only one eigenvalue, or it's a part of a system which looks something like this. Okay, so if you try to find out the two eigenvalues, you'll see that nothing really works out. And this is the case where there is one eigenvalue, but something quite bizarre happens. And if you actually try to find out the solution for this, you'll have linear terms appearing in your system rather than exponential terms. Okay, so we're not going to go into the theory, but I'm going to show you how it looks. So in order to mimic this system, C is bound to 0, B is something positive. Okay, so in this kind of system, we have one eigendirection which is 1 comma 0, which is the x-axis. Okay, the x-axis is the eigendirection. The other direction is also the x-axis, because we cannot span the entire space with just one eigenvalue. Okay, the eigenvalue are both equal and equal to -1. So the x-axis is sort of attracting all trajectories towards itself. Okay, so this is the x-axis and it's attracting trajectories towards the origin, but it's not actually going like this. No, it's not. It's actually overshooting from this and converging to the origin. Okay, the trajectories are doing this. On the other end, they're doing something like this. It's almost like it's trying to form a spiral, but it's not able to form the spiral. Even before doing a first round of the spiral, it is getting attracted towards it. Okay, so it indicates that the degenerate eigenvalue has to be something which transitions from the behavior of a spiral. So let me just change this particular value of the matrix to something so that we can make sense of it. In fact, let's see vary by 0.1 so that the small changes can be reflected. Let me run this again. Let me go back to A and D being equal to 1, and let C be something very close to 0. In fact, let us try to plot the eigen directions as well. That will be quite useful. So the eigen directions we can plot very easily with the help of the eigen vectors giving us insight into the direction. Okay, so plt dot plot x1 comma x1 times Now the direction will be simply the eigenvector. So this is the eigenvector. The direction of the eigenvector is simply v2 by v1. Okay, because this will be like v2, this will be like v1, and v2 v1 are components of some eigenvector. Okay? I'm just writing it like this. Don't be confused that v1 and v2 are the two eigenvectors. In fact, in order to avoid confusion, let me write them as v1x and v1y. Yeah, that makes sense. So this will be v1y and this will be v1x. So the slope of that eigenvector will be v1y by v1x. So we will plot on the x-axis, it will be x, and on the y-axis it will be x times this slope, and the slope will be equal to v1 comma 0 divided by v 0 comma 0. Let me plot this and see what it. Okay, so this is obviously one eigenvalue, and similarly we can, not eigenvalue, eigenvector. Similarly we can plot the other eigenvector. This will be 1 and this will be 1. Oops. So these are the two eigen directions. Let me plot this. Okay, so the green is one eigen direction, the orange is one eigen direction, and the blues are all the trajectories. Let us go back to this degenerate case. So A and D are equal. Alright. Now C's value is decreasing. So let us reduce C slowly. So at point 7, these are the two directions. Okay. So the green line is obviously repelling while the orange line is the unstable one. So in this case, the orange line is the unstable manifold and the green line is also the unstable manifold. So the origin is now uh, repelling node. It's an unstable node. Okay, because both the eigenvalues are positive. Now when I further reduce C, let's see what happens. The two eigen directions, you can see that they're trying to come close together. They're coming close. They are coming close, and so both of them are repelling. Okay, both of them are repelling. This is repelling. This is also repelling. So it's repelling like this. It's repelling towards this direction strongly. It's repelling towards this direction strongly. It's repelling like this, and like this. So now when this becomes 0, these two eigen directions have merged. Okay, so essentially these two have merged into this axis, and it's strongly repelling everywhere. So whatever this pre-merging direction was is like the behavior of this entire line. In fact, let me reduce the step size of this further, and let me make the default values as something like this. Okay, okay, so the eigenvalues, the eigenvectors have become really close, and both these eigenvectors are repelling from the origin, and once they merge they become a degenerate eigenvector case. Okay, so degenerate eigenvector case is somewhat of a transition between two repelling eigen directions, and let us see what happens when we reduce C. Okay, so then it goes to a spiral case. So forget about these errors because we're trying to divide complex numbers and all. So the errors are primarily because of this. Let me get rid of this. Let me run it again. So now when C becomes negative, it transitions into a spiral. So it's like spiral is one case, and it's a growing spiral. We have the degenerate one case and two repelling directions as one case. And degenerate sits at the boundary between a spiral system and two repelling systems. Okay, I hope it is clear by this illustrative example. Let us go to a negative value and a negative value. In this case, it will be attracting now. So it's an incoming spiral. So it's an incoming spiral, and let us now make C0 so that it becomes degenerate again. So it's trying to become degenerate. Boom, it becomes degenerate because the eigenvalues are now equal. And once I go beyond this, we can switch on the plotting of the eigen direction. Actually, plotting the eigen direction for a spiral case makes no sense because in time it's rotating. Okay? It's not fixed. So for a minus 1 and b minus 1 and c positive. So in this case, both are two attracting directions. So it's not just repelling. Okay. So in this case, these two eigenvalues are negative. So both the eigen directions are attracting, and the degenerate lies between these two cases. It lies between either a repelling and or attracting spiral, or it lies between two eigen directions which are attracting or repelling. And at the boundary of those, we have a degenerate condition. So far I've discussed how you can do all this. You can make a quiver plot, you can find out the streamlines, and they do give you an overview of what this particular two-dimensional flow looks like. But we can also perform a numerical integration and actually find out the trajectory instead of using streamline. So basically what streamline does, it uses the velocities that we have declared in all the snippets. Using those velocities, it performs an integration using the Runge-Kutta method or whatever it is inbuilt, and based on this it integrates this velocity field in time and finds out the trajectory. But in order to have a better control, we can actually solve the particular initial value problem and find out the trajectory ourselves as well without having to appeal to this particular thing. And the benefit of doing a solution by means of one of these specialized algorithms is that you can have various conditions inside the code itself. So suppose you're solving an initial value problem and the trajectory looks something like this. So you can ask the code to tell you at what particular time. So this is the x and y axis. And suppose this is x equal to 1, rather y equal to 1. You can tell the code to tell you at what time this particular event has occurred. Okay. So in time, the trajectory follows this path, and the code can actually tell you at what time event this has happened. But anyway, for now we will not require all this. Let me just grab a snippet really quick and let me show you how we can actually solve all of this using the IVP, the initial value problem solution. Okay, so this is the particular flow. So let me just run this code to make sure everything's fine. Okay, everything's fine. All right, so how does it work? Inside the scipy dot integrate submodule, the function that resides is called as solve underscore IVP, and it expects as an input a function handle, it expects as an input a time span, set of initial conditions, and various other conditions. And we'll look at the contextual help when we encode this. Okay. So we won't be needing the stream plot in this particular case. We'll only be needing we'll keep the quiver plot just in case. Okay, so we will define the right hand side. So in this case, the function that we are solving is dx dt is equal to x plus y, and dy dt is equal to 4x minus 2y. So this is what we are solving. So define my sys as, and the inputs will be time and x, and it will return these two outputs. So it will be x1 plus x0 plus x1, and it will return 4 times x0 minus 2 times x1. So essentially, the x variable appearing over here is equivalent to x0 in that particular function, and y appearing in this particular equation is equivalent to x1 appearing in this particular function. So this is what it has to return. It has to return an array of the right hand side, nothing else. Okay, so this is simply returns the RHS. In fact, it can be non-linear as well. It doesn't have to be linear. In this particular lecture, we are doing linear problems, and so it is linear. Okay, so then once we have defined the function handle, we're gonna go ahead and call the function. So before that, in fact, let me add a cell before this to import solve IVP. So from scipy dot integrate import solve underscore IVP. So now that's loaded. We can now go ahead and call this solve underscore IVP. Okay. So sol is equal to solve underscore IVP. My sys tspan, we'll define tspan and all that. ICs, so we don't have any additional arguments. So and dense output equal to true. So let me go to the contextual help and show you what these things mean. So solve IVP takes an input, the function handle, the time span, the initial condition. Additionally, you can specify what method you would like the initial value problem solver to take. By default, it is Ranskutta 45 method. And if we have time later on in this course, we will discuss the bare-bone implementation of Ranskutta method. T-eval, that is, if you want to evaluate the solution at some specified times, you can supply. We don't need to do that at this moment. Dense output is by default false. Okay, dense output is a way of sort of outputting something which is an interpolating function. So when you solve a differential equation numerically, you will obtain output at some discrete points. Okay, you will obtain outputs at this discrete point. But if you say dense output equal to true, not only will you have the discrete outputs at the specified, not specified points, at some discrete points, but if you ask the computer to give you these intermediate values at whatever times they are, it will also give you those values. So in a sense, if you say solve some other time which is other than those discrete time steps, it will give you the value of the solution at those time steps as well. So it gives you an interpolating function. Once we implement it, it will be clear what it means. So vectorized equal to false, args equal to none. So args, actually, if you have the function which takes as an input some additional parameters like a, b, then you can pass additional arguments as 1, 2, comma 1. Suppose a would be passed as 2 and b would be passed as 1. This is how you would pass them. But in this particular case, we don't have any additional arguments that we want to pass, so we don't put them. So now we need to tell this snippet what tspan is going to be. So tspan is an array which contains the initial time 0 and the final time, say 10 seconds, not the seconds but 10, the initial conditions. So in the xy plane, the initial condition x0 y0 has to be specified. Let us take a condition somewhere over here. So that point is going to be, say, minus 2.5 comma 2.5. Minus 2.5 comma 2.5. Actually, we can later wrap everything inside an interactive widget which will show us that particular trajectory given that initial condition. So in ICS will be simply minus 2.5 comma 2.5, or actually we can soft code it as x naught and y naught. So let me call it as x0 comma y0, and let x0 be equal to 2.5, and let y0 be equal, this is minus 2.5, and let y0 be equal to 2.5. Okay, so let me run this and let me show you. So after running it, there will be nothing which will be outputted, but let me show you what soul is. So soul contains all this. So because the dense output is set to be true, it says a message that the solver has reached the end of the integration steps. Number of function evaluations is 110. It gives us an interpolation object called as soul. Okay, uh, it gives us t and y arrays. Okay, so by default when we do this, it always outputs t and y. So let me plot. So essentially what will we have after solving this? We will have a time series of x as something and a time series of y as something. So we have two time series, x and y. So let me show them. Let me show them in this particular cell. Sol.t. Okay, so it contains all the different times. Then what do we have? Sol.y. It contains two arrays. One of them is x over here. One of them is y over here. So sol.0 is the x array corresponding to our solution, and 1 will be the y array corresponding to our solution. So we have to do simply plt.plot sol.t comma sol.y0, sol.t comma sol.y1, and this will give us the two time series that we're looking for. Okay, obviously it appears to be unbounded for, okay, that's, it grows quite quickly. So let us reduce the time step because it has obviously flown off into minus infinity. So let me reduce it to 5. Okay, actually the solution is e to the power minus or e to the power minus lambda t, where if lambda is quite high, then it will fly off to infinity quite quickly. So let us make it only 1. Okay? Let me make it only 1. Let me execute this cell. Okay, so x starts from minus 2.5, y starts from 2.5, and this is how the solutions converge. Okay, so apart from this, we can alternately define the t out as np.linspace 0 to 1, and say we take 100 points. Now we want to interpolate the object. So x out equal to sol.sol of t out, and y out equal to sol.sol of t out. And this has to be 1 and this has to be 0. Let us plot all of this. So plt.plot t out, x out, t out, comma y out. So the smoother curves are the interpolated objects, while the jagged curves are the outputs raw from the solver. So the solver has only made how many evaluations? I'll show you that also. So let me print. So the object has only the solver has only made 26 function evaluations. So it means that in going from t equal to 0 to t equal to 10, it only needed to make 26 function evaluations, because the Runge-Kutta solver, that is the default solver of the solve IVP function, it it takes adaptive time steps in order to find the appropriate time step to minimize the error. Okay, if it takes too large of a time step, it will induce more error into the solution. If it takes too little time step, you're not getting something which is magnificent, because there is some default tolerance of this. So if you go below that tolerance, you don't really care. You want to maintain this error reference point. So the RK45 method tweaks the time step so that it takes optimal time step. So it has to make 26 iterations in order to integrate from t equal to 0 to 1, rather this was 0 to 1, and hence that jagged line appears. But if we use sol.sol to interpolate, then we get smooth outputs. So now that I have shown you how to use the sol object, we can go back to this particular cell and we can plot the trajectory. So how do you plot the trajectory? It's simple. So it says it's simply, let me define t output again. So t out will be np.linspace 0 to np dot max tspan. I'm soft coding it because if I change tspan, I don't want to recode what uh, t out will be. Let me put 100 points. Then x out will be sol.sol of t out. So it will evaluate the solution using the interpolation object for all the t outs specified by us. Okay, these are all the t outs which are specified by us. X out will make this as the first column of x out, which is x. Then let me copy this. Y out will be the same thing but the second column. Okay, so essentially there's nothing to be confused about. T out is this array, and when you call sol.sol of T out, you get this same length but two columns. The first column, all the outputs are x values. Second column, all the outputs are y. So that is why I'm assigning all the zeros to x out and all the ones to y out. Okay, once we are done with this, we will go ahead and simply plot the trajectory. So in plotting the trajectory, time is not important, time is parameterized. So we will simply do plt.plot. On the x-axis we'll have the x points, and the y-axis we will have the y points. Let me run this. Okay, it's blowing away. So let me bind the x limits and y limits of this problem. So plt.xlim minus 3 to 3, plt.ylim minus 3 to 3. So this is the trajectory. Let me, yeah, so I don't like to have this text, so I'm going to suppress it. Okay, excellent. Now let me wrap everything inside a function so that we can pass different initial points and find out the trajectories corresponding to those particular initial points. Okay, so we're gonna wrap all of this. Let me give them an indent. So we're gonna define show traj x naught y naught. Let me give some default values of -2 and 2. So these are just the default values. We're gonna comment out this particular line. Then we're gonna write w equal to interactive show traj. We're gonna pass the function handle x naught equal to -2.5. Oh, so this has to be -2.5 to 2.5 in steps of 0.05, and y naught will be -2.5 to 2.5 in steps of 0.05. Then we're going to show the widget. Okay, so we have shown the widget. Let me change. Okay, so now this is how the trajectory appears. Okay, so over here we have changing of the branch. uh, Let me also plot the eigen vectors, so that we can clearly see how the trajectory has changed. We're gonna plot this as well. This has to be indented. Okay, let's run this. Let me change. So you see how it's getting attracted. So in order to show this better, let us plot the initial point by a small marker. So plt.plot x0 y0. Okay. Okay, so this is the initial point, and this is how the trajectory evolves. So once we cross that manifold, so once this manifold, it will go towards the origin. But once we cross it, it is now attracted towards the other unstable manifold, because as t tends to infinity, it is attracted towards the other direction, not the other direction. So it's now going towards the unstable manifold along the positive direction, positive x and y direction. Okay, let me now change y. So it's so over here it's attracted towards plus infinity, x and y going to plus infinity. As we would do this, it's again attracted to that. Okay, so with the help of this, you can clearly figure out how trajectories in the phase space look like. This will be a very useful tool to analyze various problems of nonlinear dynamics, how trajectories evolve and so on, especially in 3D. So it's worth spending some time in fooling around with various snippets. Try to do various problems, try to do the assignments very carefully. So with this, I would like to end this particular lecture. I've given you a taste of how you can analyze various linear systems with the help of Python, and the assignment will be quite entertaining, in which you will actually solve a very famous problem proposed by Strogatz, and it is called as the Romeo Juliet problem, where the level of attraction between Romeo and Juliet is modeled by means of this linear system. Okay, whether the case where if Romeo shows attraction towards Juliet, but Juliet does not show the same level of attraction towards Romeo, what will happen to that system? Or if Romeo shows some attraction to Juliet and Juliet hates Romeo for it, then what happens to that system, and so on. So it's a very famous problem, and it will help you really uh, show insight into understanding what the physical meaning of such of the evolution of such linear system means. Okay, so with this, I hope you've learned enough to analyze linear systems, because understanding this lecture and the previous lecture holds the key towards understanding whatever we're gonna study in the coming lecture, that is nonlinear systems. Okay, and this holds the key towards understanding nonlinear systems, because obviously we're gonna linearize a nonlinear system in the vicinity of a point and try to gauge whether that point has these behaviors that we have discussed in this class. With this, I'll end this particular lecture, and I'll see you next time again. Bye.